Hi everyone, in this video we'll be starting with CMT level 2 chapter number 26, and that is correlation. Before watching this video, make sure to check the chapter 25. In case you haven't, then I've linked it in the description box below. So again, we'll be referring to the notes and we will go over the textbook in further videos. But before that, you need to know that these notes have everything that is important which is given in the textbook. So this is very exam oriented. So in the previous video, we saw about R and we also saw about the R square. So we saw what is coefficient of determination. We also saw what is the Pearson's correlation coefficient. And we saw how to calculate the formulas, and we also saw how to calculate the covariance of a particular thing. And we also saw what is the formula of regression analysis, which is y is equal to bx plus epsilon. And we know that y is the dependent variable and a is the y-intercept. And we also saw how to calculate b, which is the slope of the line, and we also saw how to calculate a. So there are two types of correlation coefficients which are used. So the first thing is Pearson's correlation method. So Pearson's correlation method basically measures the strength and direction of correlation between two variables, and Pearson's correlations method is also known as the product moment correlation coefficient, and it is denoted by R, which is Pearson's correlations coefficient. So whenever we have the term product moment correlation, you need to know that it is talking about the Pearson's correlation method. The formula of Pearson correlation method is covariance of xy divided by standard deviation of x and standard deviation of y. How to find the how to find the covariance? We saw that it is the summation of x minus x mean multiplied by y minus y mean divided by n minus 1. It is the sum of product of the deviations of xy from their respective means divided by the number of observations subtracted by 1. So the values of r will always be between minus 1 and 1, and minus 1 means that there is a negative relationship, plus 1 means there is a positive correlation, and if it's 0, that means that there is no correlation between the two variables. So when I say negative relation, it means that if the x is increasing, then the y is decreasing, and if x is increasing, then y is also increasing in case of positive correlation. Now substituting the value of covariance in R, we get this formula which we anyway saw. So this also we saw. Now we know that x minus mean divided by the standard deviation. Okay, look at this. Now we have a new term which is the zx and zy. It's very simple. Zx is basically x minus x mean divided by the standard deviation of x, and zy is basically y minus y mean divided by the standard deviation of y. So these are the formulas of zx and zy. They basically represent the z scores of the x data and the y data. Now after you find the z values, what formula will you get for the Pearson's correlation efficient? It is 1 upon n minus 1 summation of zx multiplied by zy. Nothing to be confused, this is exactly what we saw. 1 upon n minus 1, where n is the number of observations, and zx and zy. So Pearson's correlation is also computed as average of products of z scores. And from the above formula, it means Pearson's correlation coefficient is valid if both x and y variables follow normal distribution. So this is very important because you need it to be following normal distribution. Okay. So how do you basically interpret the R values? If the value of R is from, one sec. If the value of R is from 0.9 to 1, then there is extremely strong price. If it's from 0.8 to 0.9, it's very strong. 0.7 to 0.8, it's strong. 0.6 to 0.7 is moderately strong, moderately meaningful, and 0 to 0.1 means that it is non-existent. Okay. Apart from normal distribution assumption, another important assumption made using R is that there exists a linear relationship between x and y. So this is an assumption which you need to keep in mind, that you are always assuming that there is a linear relationship between x and y. Pearson's correlation is not satisfactory if the relationship is non-linear. So in the case where the relationship is non-linear, there you cannot use Pearson's correlation, and there you are going to use the Spearman's correlation coefficient. Talking about Pearson's correlation coefficient, it is also known as non-parametric correlation coefficient. And non-parametric correlation coefficient, or Spearman's correlation coefficient, is denoted by the symbol rho, which looks like this. What is the main advantage of this? The first thing is that it takes into account even when there is no linear relationship between the two. And the biggest advantage is that it is insensitive to outliers, because we are not just taking the absolute values, but we are ranking it, and we are not taking the actual values, and we are going to just look at the rankings of the same. It doesn't assume any distribution of the data, and hence it is called non parametric. Why are we calling this non parametric? Because we are not taking any assumptions into account. Whereas in Pearson's correlation coefficient, we took an assumption that they are linear in nature. So that is the biggest advantage. The formula of Spearman's correlation coefficient is rho is equal to 1 minus 6 summation of d square divided by n square minus 1. Now what is the value d representing? D is the difference between the paired ranks of the data set, and n is obviously the total number of observations. Now, D is basically the difference between the rank of x and the rank of y. So, in this case, it's 1 minus 4, 3 minus 2, 5 minus 1, 4 minus 15, and so on. N is the number of observations. So, the Spearman's correlation coefficient is 1 minus summation 6 multiplied by summation of d square divided by n square minus 1. So this is the Spearman's correlation. Keep that in mind. Again, like we saw the Pearson's correlation coefficient, the Spearman's coefficient also varies between minus 1 and plus 1. So coefficient of determination, if the square of Pearson's coefficient, okay, coefficient of determination we have already seen in the previous chapter, it is the square of Pearson's coefficient, and it is denoted by r square. The meaning of the value denotes how much percentage of data variation can be explained by the correlation. Example, let r value of some data set between x and y is 0.9, then r square is obviously the square of 0.9, which is 0.81. What does this data actually tell us? It tells us that 81% of the total variation in y can be explained by a linear relationship between x and y. But the remaining 19% is basically error in predicting the variation, which may be due to exogenous factors. And when I say exogenous factors, it's because of factors which are other than x. So from the above discussions, we saw that we have taken some assumptions when it comes to the Pearson's correlation coefficient, or the coefficient of determination, since both of them are calculated using the Pearson's method. The first thing is linearity, which means that we just assume that both the variables have a linear relationship between each other. And the second thing is we are considering that it is always given in a normal distribution, and there is a normality factor in whatever examples we are taking. And there is no outliers effect, which means that there are no exogenous factors, but that's not realistic, because in real world and in the real market there are exogenous factors. So linearity. In real world, it is very rare to see a good linear relationship. Always look at the scatter plot to check if it appears linear or not before. So before you actually find the R value, you need to see if there is a linear relationship or not. Because if there is a linear relationship, if there's no linear relationship, then you can't use Pearson's method, because it's going to give you a wrong answer. So sometimes if scatter plot shows reasonable linearity within certain range, grouping of data is utilized and fit varying regression line. So look at the diagram which is there. In this scatter plot, we can intuitively group the data into two groups, and then we can fit two separate linear lines. However, such grouping may not make any sense when dealing with time series. Typically, market data is time sensitive, but it may be possible to group data, time work, but not rank wise. In such case, we can still use Pearson's method of correlation because we are able to group it. Now, there are other methods that are more complex but can be better accurate to use, like kernel regression and the neural networks methodology. These are not normally utilized for general market analysis purposes. Talking about normality. While Pearson's correlation method assumes normal distributions, Pearson's method doesn't assume normal distribution. It is very difficult to find 100% accurate fit of data to normal distribution. However, it is often observed and hence preferred to use daily or weekly changes instead of the raw data because that data usually approximate to normal distribution. Talking about outliers, when using linear regression equation for predictions, one should check for sensitivity of the model with respect to outliers. Because if it's highly sensitive, then maybe Pearson is not a good method to use. It is customary to delete a few outlier points and to check if regression line altered significantly or not. Look at the first diagram. This is after selecting the outlier. You can see a point which is much far from the linear regression line. In the second one, you can see that the regression line didn't alter much, even if you take into account the outlier, right? It's the same thing, so it is safe to use. However, if you see the other one, you can see that there is a significant difference between the linear line, between these two, between these two, this and this. So in that case, it is very unsafe to use it. Now we come to what is homoscedasticity. Homoscedasticity is basically a very important factor which is used in statistics again. So talking about it, in using R square or rho for correlation coefficient estimates, it is usually assumed that variation in data of x and y are more or less equal. If not, then the analysis will be invalid. Now, what exactly is rho? Let's talk about that again so we can understand this better. So, the difference between Spearman's correlation coefficient rho and the Pearson's correlation coefficient, now it's very clear and we know the difference between it. Now we can go back and let's see what hypersensitivism is. However, in many cases, the data can be transformed into other forms like logarithmic or squares and etc. And then after you transform it into those formulas, then you can basically use regression analysis because the kind of transformation can remove the violations with homoscedasticity. So I hope you understood what homoscedasticity is, right? So in that case, you are basically first converting the data before you actually start using the regression analysis. So again, this is a simple chapter. The only thing which is confusing is you need to know the difference between both the methods and you need to learn the formulas of the same.